Okay, so this is my Module 3 presentation in regression on coding and generalized linear models. So the first thing I wanted to do was introduce our data set. And so this data concerns horses. So we have two continuous predictors, pulse and respiratory rate, and we have one categorical predictor, which is temperature of the extremities of the horse. And this categorical predictor has three groups, cool, normal, and warm. And we have our binary outcome variable, which represents the survival rate of horses. So 1 represents if the horse lived, and 0 represents if the horse died. So to take a closer look at our outcome variable, as you can see, we don't have a normal bell-shaped curve. Rather, we have this bimodal distribution where we only have zeros and ones. And so in regression, we use regression to reduce our uncertainty about our outcome variable, but when we have this bimodal distribution, we can see that our best guess about the mean will likely not tell us much about our outcome variable. And so that justifies the use of a different type of model than OLS, such as logistic regression. And the other important thing to note here about our outcome variable is that our mean is about 0.6. So it falls in that middle range, and that means that it's not a zero skewed outcome. And this is important because we have to make sure that we are appropriately using logistic regression, and logistic regression is really only going to be appropriate when you have a relatively even distribution. And so that would mean a mean between about 0.4 and 0.6. So before we can run any models, we first have to code our categorical predictor. And coding allows us to convert categorical data into numeric data. And so we've used dummy coding, which is the default in R. So once we set our categorical variable as a factor, it is dummy coding, and we can produce this contrast matrix, which shows us our comparisons. So in dummy coding, we are always making comparisons between the base group and all other groups. So cool represents our base group, and as you can see, we have k-1 levels. So we have 2 levels because we have 3 groups. And something else important to note about dummy coding is that the codes are orthogonal, which means the sum of the cross products is 0. However, they are not centered like they might be in the case of effects coding, which might be an issue when we are interpreting interaction effects. However, we were most importantly interested in comparing to the base level, so we used dummy coding. So first I've run my ordinary least squares regression, and in our output, although we can see we have some significant values and we've reached significance for some of our predictors, we must take into account the potential for errors in this output when our data are non-conforming. And so because we have an outcome that is binary, it gives us standard errors and residuals that are essentially uninterpretable. And to demonstrate that a little more clearly, I've run some diagnostics. And so from looking at the diagnostics, we can see why running linear regression on this data set violates several of the assumptions. And the first thing is heteroscedasticity. So in logistic regression, we'll have inherent heteroscedasticity because we'll have different error variance for each different value of the predicted scores. And so this means that we're no longer interpreting that variance accounted for like we would be in OLS. And we can also see that our errors are not normally distributed. We can see by looking at the normal QQ plot, and this is because our dependent variable is not continuous. So because of this, we need to use a model that allows us to deviate from Gaussian normal assumptions, such as logistic regression. And so to compare these two models a little more explicitly, First, we can talk about the general linear model versus the generalized linear model. So the generalized linear model allows us to go beyond OLS and beyond these assumptions. So the Gauss-Markov assumptions, aside from independent residuals, we should not have in logistic regression residuals that correlate with our outcome variable, but we will have heteroscedasticity, and we obviously do not have a continuous dependent variable or normal distribution. And importantly, one similarity between logistic regression and OLS is that all the predictors will be entered simultaneously, which means multicollinearity will become an issue, especially when we have an interaction effect. And so to combat that, I've centered my continuous variables to eliminate some of the multicollinearity. And then finally, our regression coefficients in logistic regression will be log odds. And also we will see z values when we test for significance rather than t values. So here I've run my model again, but with the logistic regression. And so as you can see, we have respiratory rate, pulse, and then our categorical variable temperature, and then an interaction between pulse and our categorical variable temperature in our model, similarly to in OLS. And the first thing we need to talk about before we get into the parameter estimates is odds. So as I mentioned before, the estimates will be log odds ratios. And so odds represent the probability of something being the case over the probability of it not being the case. So P over Q. And because this is difficult to interpret in terms of the natural log, we will take the exponent out to get just an odds ratio. And so the other thing that's important to note about the odds ratio, or P over Q, is that it adheres to the law of total probability. So that means that P plus Q, so the probability of an event occurring plus the probability of the event not occurring, equals 1. So all outcomes of the event must sum to 1. And so ideally, if we get the probability of something occurring to be greater than the probability of it not occurring, we will have P greater than Q. And also, what's important to note about this equation, P plus Q equals 1, is that also means that Q equals 1 minus P, which will become important later on when we're interpreting our coefficients. So now we can get into interpreting our coefficients. So the first is respiratory rate. And so respiratory rate does not contribute significantly to predicting whether or not a horse survives because the p-value is not significant at the 0.05 level. However, pulse does contribute significantly to predicting whether or not a horse survives at the 0.05 level. And so the regression coefficient here is negative 0.03. So this means that for every single point increase in the pulse of the horse, the natural log odds of a horse living decreases by 0.03, holding all other predictors constant. So now we can calculate our exponent of this coefficient because the natural log is difficult to interpret and we don't really know what that means. So we'll take the exponent, and what we can see from that is that if our odds ratio is bigger than 1, that means the odds increase, and if the odds ratio was less than 1, that means the odds will decrease. So in the case of pulse, we can see that the odds ratio is equal to 0.97. So if you remember the law of total probability, this would mean that for every single point increase in the pulse of a horse, the odds of the horse living decrease by 3%. So now we're going to move into interpreting these categorical results. And to do that, I've written out our regression equation to help us understand the parameters a little more clearly, especially with our interaction, and also equations for understanding what these categorical codes even really mean. So essentially, when we're looking at this parameter estimate for normal temperature, it is really a comparison of the odds of survival for a normal temperature horse over the odds of the survival for a cool temperature horse. So if you remember, we used dummy coding, and so that coding matrix is what allows us to help interpret our results. And so when we take the exponent of this log odds ratio, which we're comparing to the base level group, we get 4.09, and that means that a normal temperature horse is 4 times more likely to survive than a cool temperature horse. And we can do the same thing for warm temperature horses and for this factor, and we have taken the exponent of the log odds ratio to get an odds ratio of 5.06. So the odds of survival for a warm temperature horse over the odds of survival for a cool temperature horse is equal to 5, which means that a warm temperature horse is 5 times more likely to survive than a cool temperature horse. And so now we can next look at our interaction results. So when we run an interaction, we're seeing if the interaction has an impact over and above the prediction of the main effects. And so the interaction term for normal and pulse represents the difference between the log odds ratio corresponding to a 1 unit increase in pulse amongst cool temperature horses and the log odds ratio corresponding to a 1 unit increase in pulse amongst the normal temp horses. And similarly, the same thing for warm temperature horses. However, as we can see, we have not reached significance for either interaction effect, and this is kind of expected because the partitioning of variance occurs simultaneously, so it is unlikely that we would see significant effects for an interaction term. And the next thing we can interpret is our confidence intervals down here. So OR represents odds ratios, and then we have 2.5 to 97.5, and that represents our confidence interval. So calculating confidence intervals just gives us another opportunity to test for significance of the predictive factors of the survival rate of horses. So if you remember, when we test just raw data, 0 would be used as the null hypothesis in a confidence interval. However, for the odds data, we reject the null if 1 is outside of the interval. And so, as you can see, the confidence interval results correspond to the significance level we observed in the output. So we can see that pulse is significant because 1 is not present in the confidence interval, as well as the normal is significantly different than cool, and warm is significantly different than cool for our group levels. And finally, we can plot a prediction model, and this really helps to kind of sum up all the results that we've seen. And so using ggplot allows us to convert probabilities by getting a prediction. So our slopes represent predicted probabilities. And so what we're looking at here is the relationship between y hat, or the chances of survival, or the probability of living. And we are looking at this relationship with temperature of extremities and pulse. So as you can see, horses with warm temperatures and low pulse have the highest chance of survival. And as temperature decreases and as pulse increases, our chances of survival for the horse will decrease. So the probability for survival is much lower for horses with a high pulse who have low temperatures. And as you can see, we've also run this on our model that has an interaction. So we're looking for changes in slopes, but we did not have a significant interaction effect. So the change in slope here is really not significant. So overall, just to sum up, we wanted to talk about some implications of using logistic regression. So first of all, we have to be really careful with the cases in which we will use logistic regression. So it's really not helpful unless it is a binary outcome, and also that binary outcome is not skewed in either direction. And so this makes the generalizability and usefulness of logistic regression more difficult. We also have to be careful in identifying those cases in which logistic regression will be practical, such as if we would have nested data or effects of time, we might use something like random coefficients modeling, or if we wanted to test several relationships simultaneously, we might use something like path analysis. And then also, as we learned from Press and Wilson that I mentioned earlier, we can use logistic regression in those cases of non-normality violations. So with maximum likelihood estimators, it is useful to use logistic regression when we have that violation of normality. But finally, we have to be wary of how useful regression models really are. So as Friedman points out, good design and proper data collection, and then modeling the data based on that will be most critical. So we can't make assumptions about the data before we've collected it. So Friedman suggests that once we collect the data, then we can make the assumptions and then model. However, he does note that assumptions are often difficult to test. So overall, good design always wins.